Okay, strap yourselves in, folks, because today we are diving into the deep end of physics. We're talking about the kind of mind-bending stuff that'll make you question reality, and trust me, you are going to want to stick around for this one. One of our listeners sent us this email, and it is just jam-packed with seriously thought-provoking questions. We are talking about linking up ideas that you would think are like light years apart, but thankfully, we've got our expert here to guide us through the theoretical wilderness. So, shall we jump right in?
Let's do it.
Okay, so first up, the listener poses this really interesting analogy. They ask, what if we think of quarks, which are, those super tiny particles that make up, well, everything. What if we think of those quarks like tiny little zygotes in the universe's grand scheme of things? Get it? Because they're like the building blocks.
Right, like the fundamental seeds of matter. And what makes this analogy even more intriguing is how the listener connects it to the Higgs field.
Oh, yeah, the Higgs field. Now, that's a name I haven't heard in a while. It's like that cosmic syrup that gives particles mass, right?
That's one way to think about it. But the listener takes it a step further. They're asking, what if it's not just about giving mass? What if the Higgs field is also actively shaping how these fundamental particles, these quark zygotes, are actually forming and interacting?
Okay, well, hold up a second. So instead of the Higgs field just being like this passive cosmic syrup, we're saying it could be more like a cosmic mold, like it's guiding how things come together at the smallest level.
Yeah.
My mind is already starting to melt.
It's a bold proposition.
Yeah.
And it speaks to this really cool concept in physics called emergence.
Emergence, okay.
Yeah, so basically emergence is the idea that complexity can come from simpler parts interacting in, well, unexpected ways. Think about it. You've got ant colonies, right? Incredibly complex societies, but each individual ant is just following a relatively simple set of rules.
Yeah, never thought about it like that.
Or take the human brain, billions of neurons firing, creating consciousness, thoughts, emotions, all from these tiny electrical and chemical signals.
And now we're saying the Higgs field might be doing something similar, but on a universal scale.
That's the question the listener is raising. It's like they're suggesting that even the most fundamental forces in the universe might be playing a role in this grand process of emergence.
I'll be honest, I need a minute to process that.
It's a lot to take in.
It really makes you wonder, though, doesn't it? What if the very laws of physics are more about fostering this kind of mind-blowing complexity than we ever imagined? I mean, I thought baking a cake was complicated, but this is next level. Okay, before I spiral into an existential crisis, let's move on to the next head-scratcher, shall we?
Absolutely, because this next one, this is where we really start diving into the deep end.
Oh, I am ready. I brought my theoretical floaties and everything.
This one is going to take us even further down the rabbit hole of theoretical physics.
Perfect, because I brought extra snacks. Okay, on to the next question from our intrepid listener. And this one takes us even deeper into the world of, well, quarks. Remember those?
Back to the building blocks of the universe.
Exactly. But not just quarks. Oh, no. This question throws something even weirder into the mix. Something called spectral particles. And I'll be honest. This is where I start feeling like I need to go back to physics class.
Yeah.
But thankfully, our expert, well, they speak fluent science.
I try my best.
So help me out here. What exactly are these spectral particles? Are they hanging out with the quarks at the quantum level?
Okay, so you're right to point out that this is where things get especially complex. And even in the world of physics, these spectral particles, they're not exactly a universally accepted concept.
So we're going rogue already.
In a way, yes, but that's what makes this question so interesting. The listener is drawing this fascinating parallel between these spectral particles and something we do know about, quarks, specifically their color charges.
Okay, time out. Color charges. Now, I vaguely remember this from, like, high school physics. Quarks, they make up protons and neutrons, right?
That's right.
But color charge, are we talking like actual colors here? Red, blue, green?
It's a great question because it highlights how physics can sometimes borrow these familiar terms, but then give them a whole new meaning. When physicists talk about color charge with quarks, it really has nothing to do with actual visual color.
So not like picking out a nice shade of quark for your living room.
Not quite. It's more of an analogy to help us wrap our heads around how these tiny particles, these quarks, are interacting with one of the fundamental forces of the universe, the strong force.
Okay, the strong force, right. That's the one that holds the nucleus of an atom together, like glue, right?
Exactly. And it's through this color charge that quarks are able to interact with that force.
So it's more like quarks have their own special language.
Right.
And this color charge, it's like the grammar of that language.
That's a really great way to put it. And what's fascinating is that our listener is making a connection between this grammar of quarks, this color charge, and the properties of these theoretical spectral particles.
They're looking for patterns, like a code hidden in plain sight.
Precisely. Now, whether that connection holds up under scrutiny, that's still very much up for debate.
Ah, the joys of theoretical physics. Always another layer to uncover.
But it's that kind of outside-the-box thinking that often leads to new discoveries.
I like it. It's like they're saying, hey, what if the rules that govern these teeny tiny bits of matter, what if those rules are actually reflections of some deeper mathematical structure, some grand cosmic equation that we're only just beginning to understand?
It's a tantalizing possibility.
And speaking of math, can you believe we're about to talk about the Riemann Hypothesis? This is big league stuff.
It's a pretty famous unsolved problem.
That's an understatement. It's like the holy grail of unsolved math problems. Mathematicians have been wrestling with this thing for over a century. And how on earth, how does it connect to all of this, to the quarks, to the spectral particles?
Well, this is where our listener makes a truly bold leap.
Okay, hit me with it.
They suggest that the solution to the Riemann hypothesis, this purely mathematical puzzle, they suggest it might actually be found, encoded, in the energy levels of quantum systems.
Hold on, I need to sit down for this. So you're saying all those headaches I got in calculus class, those were actually glimpses into the fundamental fabric of reality.
It's a bold proposition.
My mind is officially blown. Can we get that in writing? I'm going to show my old math teacher.
I'll see what I can do.
Okay, I'm still trying to wrap my head around that whole Riemann hypothesis thing. I mean, who knew math could be so, well, trippy? But our listener's next question, it takes us from the mind-bendingly small to the mind-bendingly massive. Black holes.
Everyone's favorite cosmic enigma.
Right. They're like the ultimate cosmic vacuum cleaners. Nothing, not even light, can escape their gravitational pull. But forget everything you think you know, because this question, it throws a real curveball into the mix. What if, and I'm just going to say it, what if the universe itself is pixelated?
Now we're getting into the realm of quantum gravity, where even the nature of space-time gets a little, shall we say, fuzzy?
Fuzzy. Okay, I can dig that.
So imagine instead of space-time being this smooth, continuous fabric, it's more like a digital image.
Like with pixels.
Exactly, like tiny indivisible units of space and time.
Okay, so picture zooming in on your computer screen, right, until you see those little squares. But instead of your screen, it's like the entire universe. And this isn't just some sci-fi idea. Physicists actually think this could be true.
It's one of the leading contenders when we're trying to reconcile general relativity with quantum mechanics.
Okay, so black holes. How does a pixelated universe, how does that change things?
Well, think about how we understand gravity now.
Okay, gravity, right.
Einstein taught us that gravity is all about the curvature of space-time. Massive objects that create a sort of dent in this fabric, and that's what we feel as gravity.
Right, like a bowling ball on a trampoline.
Exactly. But now imagine that trampoline is actually made up of these tiny little squares.
Okay, I'm picturing it.
If space-time is fundamentally pixelated, there's a limit to how small those dents can get.
So you're saying there's like a minimum size limit for a gravity well?
In a way, yes.
But what does that even mean for something as extreme as a black hole?
Well, at the center of a black hole, according to our current theories, there's something called a singularity.
Ah, yes, the singularity. That's where all the laws of physics go to, like take a vacation, right?
Pretty much. It's a point of infinite density where our understanding of physics just breaks down.
So no souvenirs from the singularity gift shop.
Not that we know of, but here's the kicker. If space-time is pixelated, that throws this whole singularity idea into question.
Wait, really? So no more points of infinite weirdness?
It's possible. Some physicists believe that a quantized space-time could actually prevent singularities from forming in the first place.
Okay, so black holes wouldn't have singularities. Then what's at the center?
That's the million-dollar question. It's like our listener has uncovered a loose thread, and suddenly the whole fabric of our understanding of black holes might be unraveling. What happens to the infinitely dense point at the center of a black hole if you can't have anything smaller than a pixel of space-time? It's a question that has physicists scratching their heads, and it could lead to some truly revolutionary new theories about the nature of gravity, black holes, and even the universe itself. Honestly, this is what makes these deep dives so exciting. It's like we are peering right into the edge of human knowledge, and your questions have helped us push that boundary even further today. Thanks again for listening, and remember, in a universe this strange, the only dumb question is the one you don't ask.